Hi, so have you ever wondered how a website with millions of users manages to almost instantly tell you whether a username is available or not? So, how do they do it? Well, one answer is the utilization of Bloom filters. Bloom filters are a probabilistic data structure, which means they depend on some amount of chance, like skip lists, and this allows them to be very space efficient and fast. They are particularly useful in reducing database query operations by storing data directly on the server side due to the space efficiency they are able to introduce. Bloom filters are also quite similar to hash tables, but instead of storing actual elements, what they do is that they hash elements to index positions in bit arrays, only storing the 1 and zeros, indicating whether an element was registered to the main database or not. But with hashing introduced, how do we deal with the problem of collisions? A one-to-one mapping would require us to create an array of the size of the hash space itself, which would be huge. So to this end, what we do is that instead of increasing the bit array size, we increase the number of hashes and allow for some collisions ourselves. The small compromise allows this data structure to tell us whether something is not present in the database, for example, a username or a password, with almost 100% certainty. While with a small error, it might also tell us that something is present in the database, even though it may not be. So let us look at some circumstances where this may be useful. So to demonstrate the power of this seemingly simple data structure, we created two applications. So for one of our application, we demonstrate a password protection application, which basically checks whether a password is safe to keep against a database of millions of passwords that have been previously breached. And another one is a plagiarism detection application, which basically checks whether a given text is plagiarized or not. So let's go ahead with the password protection. So for this, we used a database of about 306 million passwords, which was about 11.5 GB, and we took a chunk of 10 million passwords from it, which was about 390 MBs, and we applied a Bloom filter to it. And we can see that the resulting filter is only about 11 MBs in size, which is about 30 folds lesser than the database. And we use this database to check we use this filter to check whether a password is present in the database or not. So let's demonstrate that quickly. So let's try some common password, and it will tell us that this password has been compromised and it might be there. This was a password that I kept a very long time ago, and as we can see that this password has also been compromised. But maybe let's try something different, and it tells us that the password is safe. Or maybe let's go with this, and the password is safe to keep. So here we have some details of the capacity of the bit array that's being used, the allowable error, which is 1%. So in 99 there's a in 99 attempts there's a 1% chance that a password might not be present, but it might be telling us that it's present there. But I fail to see how that would be harmful. So for our next application, the plagiarism detection application, we utilized the BBC text database, which consisted of extracts from BBC reports and articles. The database was about 4.9 MB in size, and our Bloom filter reduced it to a mere 77 KB. And to detect for plagiarism, what we did was that instead of hashing words, which would definitely get matches in any document, what we did was we hashed complete sentences, and then we matched whether the hashes of two sentences were matching to check for plagiarism. Obviously, this wasn't a highly ideal approach, it was more of an experimental one, but the results were still nonetheless promising. So let's go ahead and check this. So as we can see that this document was only about 7% plagiarized. Whereas in actuality, this document wasn't at all plagiarized, but we see that there is still some discrepancy, and this is likely due to the limits of our hashing algorithm, which is limited to 30 bits. And we believe that if we used an hashing algorithm such as a 128-bit hashing algorithm, then this value would have been more close to 0. But still, if we see that if we try something that actually was plagiarized and see the results, then in that case we can see that the results are considerably promising, and we see a 69% plagiarism, which is roughly about the ratio of plagiarism I had by default added to that document. One last thing we did was that we performed hash testing for the hashing algorithm we implemented. So obviously hashing was an important part of this project throughout. So we compared two hashing algorithms, the Adler32 checksum hash and the Murmur3 hash, which turned out to be the better option. So as we can see that the average bit change in each value for a random set of strings was about 50 for the Murmur hash, showing that it was well spread. Furthermore, the number of collisions while generating a filter by the Murmur hash was only 3. Whereas when testing the Adler3 hashing algorithm, we can see that the average bit change for a random set of about 10,000 strings was only 26%, which reflects that the algorithm doesn't spread out its outcomes that well. And this was also reflected in the number of collisions that were generated while generating a filter, which accounted to 116 in comparison to the Murmur 3, which only had 3.